Alrighty, this is going to be a quick walkthrough on how to do the math for the salvage project. We're going to have a separate video for the pontoons and for the main vessel. This one is going to be about the main vessel. So the first thing we're going to have to calculate is the weight of the vessel, the weight of all the metal in there. That we're going to do by looking at the 11 individual panels of metal, calculating their square area, and then seeing how much that is going to weigh based on how much we know a single square foot of metal weighs. Next, we're going to look at the lift capacity or the buoyancy of the empty air pockets at the stern and the bow of the boat. Next, we're going to calculate the floodable volume of that middle section in between those two air pockets. Now, normally for floodable volume, we would calculate this in cubic feet. However, we're going to be converting that into gallons because for this project, what we need to figure out is how long is it going to take for us to pump all that water out, and that math does need it to be in gallons to work. Next, we'll be calculating how much lift we need to lift that boat. Essentially, we're going to calculate how much the vessel weighs, and then how much the water weighs, and sort of think of it as negative weight. We're going to find the difference there and see how much we actually need to pull up on this boat to lift it out. And then finally, we're going to use that information from the floodable volume to calculate how long it should take us to drain all that water out. So starting off with the weight of the vessel, we're going to look at each of these individual panels, not one by one, but most of this math you can just kind of copy and paste. Since if you measure like this wall right here, this wall is identical, so you've already done the math for both of these. So we're going to look at 11 pieces. Indeed, there are 11. Pause if you need to see what's what. So for the pieces that are perfect squares or rectangles, it is going to be the same math. We're going to multiply the length times the width to find the total surface area. This is the width, this is the length, and for this example, this right here is piece number 9, the deck, kind of the bottom. We know that it is 10 feet wide and 20 feet long, so if we multiply 10 times 20, that gives us a total surface area of 200 square feet. For the two hatch walls right here, the walls with a big old hole in them somewhere, that math is going to be a little bit different. So we are still going to calculate how much surface area we have for the wall, just like we did for the deck. However, we are going to subtract how much area this hole has. So first off, we know that this wall is 10 feet wide and 5 feet high. If we multiply those numbers together, we know the surface area of the wall without the hole is 50 square feet. Once we calculate the area of the hole, which is going to be 3 feet by 3 feet, we know that the hole has an area of 9 square feet. So if we subtract the hole from the main piece of metal, we get a remaining surface area of 41 square feet. And then finally, for those two trapezoid-shaped pieces, basically the port and starboard walls, the math there is going to take a pretty simple formula. It is the top edge plus the bottom edge divided by 2, and you multiply that number by the height of these shapes. So we know the top edge is 25 feet long, the bottom edge is 20 feet long, and it is 5 feet high. So essentially that equation is going to look like the top, 25 feet, plus the bottom, 20 feet, divided by 2 times the height, 5 feet. So the first thing we're going to do is we're going to simplify this fraction right here. We're going to do that by adding 25 to 20, which is going to give us 45. So now we have 45 divided by 2 times 5. Next up, the next step is we're going to actually do this math right here, divide 45 by 2, and that will give us 22.5. And now the last step in this equation is multiplying 22.5 by 5, which gives us a total square footage of each of those trapezoidal pieces of 112.5 square feet. So once we do the math for each of those pieces, we end up with these 11 numbers. To find the total surface area for the entire vessel, we're just going to add those together, which gives us a total surface area of 868.6 square feet. Now we're going to use this information to calculate the weight of the vessel, and that's pretty simple. We find out how much does 1 square foot weigh, and we multiply that by how many square feet there are. So we know there's 868.6 square feet, and we know that mild steel, which is the material that this boat is made of, weighs 5 pounds per square foot as long as it's 1/8 of an inch thick. So if it is more than this, it's going to weigh more. we know that our hull is 3/8 of an inch thick. That is 3 times as thick, which means a square foot is going to weigh 3 times as much. So 3 times 5 is 15 pounds. 3/8 of an inch thick means it is 15 pounds per square foot. So the equation here is pretty simple. Multiply the weight, the 15 pounds per square foot, times the total surface area, the 868.6 square feet, and that will give us how many pounds the vessel weighs. So we have 15 times 868.6 equals 13,029 pounds. The final step here is, as our instructor told us, to add 1,000 pounds to cover all the miscellaneous parts, which means the total weight of the metal in the vessel is 14,029 pounds. So now we have one of our 5 bits of information. Next up, we're going to calculate the lift capacity or the buoyancy of those empty air pockets at the front and back of the ship. So to do that, essentially what we need to do is sort of imagine joining these two pieces together, kind of like rotating them around a bit to smash them together and make a big rectangular shape instead of these two weird trapezoidal shapes, right? So we're going to measure the top and bottom edges on one side, and we know, even though they don't look like it in this picture, we know that these are actually identical, and so essentially it's going to make our math a little bit easier. So we're going to add the top number of one side to the bottom number of another. It doesn't matter which way you do this. It could be the top of this one and the bottom of this one, or the top of this one and the bottom of this one. Because they are identical, it does not matter. So we know that that number, these two added together, is going to be 4.18 feet. So essentially, think of a big rectangle that comes out 4.18 feet and then comes down 5 feet, because we know the height of the vessel is 5 feet. So if imagine the little kind of the rectangle we just made is 5 feet high and 4.18 feet wide. That is going to give us a total surface area of 20.9 square feet. Now, to turn that from surface area into the volume of the entire 3D shape, we're going to multiply that surface area by how deep it is, how wide it is. We know this is 10 feet wide, so we're going to take our 20.9 square feet surface area that we got from that imaginary rectangle we just made, multiply it by 10, and that gives us 209 cubic feet. So we now know how much air is inside these. Next up, to find out how much buoyancy that's going to give us, we are going to multiply the weight of 1 cubic foot of the surrounding water by how many cubic feet of space there are inside these. Since this is a freshwater lake, that number, the weight of the cubic foot of water, is going to be 62.4 pounds. So we multiply the number of cubic feet by the weight of a single cubic foot, and that gives us a buoyancy of 13,041.6 pounds. This is the buoyancy of the vessel. Next up, we're going to calculate the floodable volume of that middle section right here. This one's pretty simple. We just multiply the length by the width by the height of that section. However, remember, we are not calculating the entire length of the bottom because there's a little extra space from those air pockets at the front and the back. So this is going to be a little bit less than the 20 feet of the entire length of the vessel. So we know the vessel, the whole thing, is 20 feet long on the deck. And we know that each of these little air pockets has a bottom length of 0.84 feet. So we're going to subtract these two sections from the length of the whole thing, and that will give us the remaining length of just the middle section. So we know that 0.84 and 0.84 equal 1.68. 20 minus 1.68 gives us 18.32 feet. That is the length of this middle section. So we know with a height of 5 feet, a width of 10 feet, and a length of 18.32 feet, all we have to do is multiply the 3 of those numbers together, which gives us a grand total of 916 cubic feet of floodable volume. Now, we have to convert this into gallons. The way to do that is to multiply how many cubic feet you have by how many gallons are in a single cubic foot, which is 7.4805 gallons. So the number of cubic feet times how many gallons are in a cubic foot equals 6,852.16 gallons. So now we know the floodable volume in gallons. Next, we're going to calculate how much lift we need, how hard we have to pull up on this boat to move it upwards. That one's going to be pretty simple. All we have to do is take the weight of the vessel minus the buoyancy of the vessel. So this is how much the metal's pushing down, this is how much the air is pushing up, and so the remaining value is 987.4 pounds. This is how much how much force we need to pull up on the vessel to raise it, not counting how much we need to pull it out of the mud suction. So we know we need at least 987.4 pounds of lift, plus, again, however much we're going to need for the mud suction. Finally, let's calculate the expected drain time, how long it's going to take to pump out all that water. So we know that we are going to be using 2 water pumps. Each one of those water pumps can move water at a rate of 290 gallons per minute. And so with 2 of those, that means we have a total rate of 580 gallons per minute that we can pump out of the middle. So we're going to divide the total amount of water that we have by how fast that water can be pumped out. We have 6,852.16 gallons. And we can pump that out at 580 gallons per minute, which means it should take us 11.814 minutes, or 11 minutes and 49 seconds. So that's how long it should take to pump out all that water. And we now have all 5 of the numbers that we needed for the main vessel. In the next video, I will talk about what to do for the pontoons.